theorems on vector space. First theorem, let V be any vector space, and for any vector u bar belongs to V, and any scalar, for any scalar, say for any scalar k, prove that, number first, 0 into u bar is equal to 0 bar. Number 2, alpha into 0 bar is equal to 0 bar. Number 3, minus 1 into u bar is equal to minus u bar. And number 4, if alpha into u bar equal to 0 bar, then either alpha is equal to 0 or u bar is equal to 0 bar. Okay, so we want to prove this. So what is given here? The given V is any vector space, given V be any vector space and let u bar be any u bar belongs to V, and alpha be any scalar, say alpha belongs to R, a real number. So, and we want to prove this first. 0 into u bar is equal to 0 bar. For example, if we take any example, say here I am writing one example. Say if you take here, say V is equal to R square, and if you take here u bar is equal to 2 3, then 0 into u bar is equal to 0 into 2 3 is equal to what? 0 into 0, and which is nothing but the 0 bar. So if you multiply any vector by 0, then we get 0 bar. So this is what V is a what? R square vector space. Take one more example. If we take here example, say V is equal to R plus set of all positive real number, and define x plus y, x bar y bar is equal to xy, and and x alpha x bar is equal to x raised to alpha. Then here, as we know that the 0 bar is 1. 0 bar is what? 1, because here if we take x bar into plus 1 is equal to what? X into 1 is equal to what? X. So x bar into 0 bar, here x bar into 0 bar is what? 1. So here 0 bar is 1. Now if we take here 0, if in place of alpha if you write here 0 and let x bar be any vector, then what is here given? The operation is given x raised to alpha, so it is x raised to 0, which is equal to what? 1. So if you multiply any non-zero vector by 0, then we get it is equal to what? 0 bar. This is nothing but the 0 bar for vector space, for this vector space V is equal to what? R plus. Similarly, you can check here for R square, let u bar is what? 2 3, and if we multiply 0 into u bar, we get 0 bar. But we want to prove this. So to prove this, now let consider 0 into u bar. But as we know that 0, we can write 0 is equal to 0 plus 0 into u bar. Why? Because this is what the property of real number, or say field. As in real number, 0 plus 0 is equal to what? 0 in real number set. But by using since V is a vector space, and by using the property alpha plus beta u bar is equal to we can write this as, or by using, I am writing the different color here, say alpha into, I am going to use here alpha plus beta u bar is equal to alpha u bar plus beta u bar. By using this property, say m2, we can write this as 0 into u bar, I am writing here 0 into u bar plus 0 into u bar. Okay, on this side, on the left hand side, it is what? 0 into u bar. Now so Now next, now since V is a vector space, this 0 u bar this here by using m2. Okay, now since 0 u bar is lie in V by using C2 by closureness property. So and V is a vector space means what, there exists a negative element of 0 u bar, so we add negative element on both sides, so we get 0 u bar plus minus 0 u bar is equal to 0 u bar plus 0 u bar minus 0 u bar. Okay, now by using associative by using a2 property, what is a2 property, associative property, we can write this as 0 u bar plus 0 u bar plus minus 0 u bar. Now since these are the additive inverse, hereby we apply here a2. Now since these are two are the additive inverse, 0 u bar minus 0 u bar is the additive inverse of 0 u bar. So by using the property, as we know that, I am writing a different color here, say since we know that the u-bar plus minus u-bar is equal to what, 0 bar. So by using this property we can write this is what our a3 property by using a4 property. So we can write this as 0 u-bar plus 0 bar. Okay, on this side it is also what, 0 bar. So but again by using property here, I am writing by using property a4. Okay, additive identity. Now by using the property, say 0 u-bar plus 0 bar is equal to what, 0 bar u-bar. Okay, this is what additive identity. So here if we add 0 bar to any 0 bar to any vector, then we get again the output is what, 0 u-bar. So 0 bar is equal to what, 0 u-bar, and this is what we want to prove here. So I am writing this proof again. Okay, so first again you can see here 0 u-bar is equal to 0 plus 0 u-bar. By using m2 we can write this as 0 u-bar plus 0 u-bar, and since by on both side if we add additive inverse, say 0 u-bar plus 0 u-bar plus, if we add both side by negative inverse, minus 0 u-bar, then we get here 0 u-bar plus 0 u-bar negative, so it is plus minus 0 u-bar. Now by using associative property we can write this as 0 u-bar plus 0 u-bar plus minus 0 u-bar. Now no need this sign. So now this is what we add the additive inverse. So the output of here on the left hand side, it is what, it is 0 bar, and here also 0 u-bar plus 0 bar is equal to what, and this is nothing but 0 u-bar, because if we add additive for any vector, then we get the output same. So 0 u-bar is equal to what, 0 bar. This is what first proof. Now second proof, what we want to prove here in the second, we want to prove here alpha into 0 bar is equal to 0 bar. Alpha into 0 bar is equal to 0 bar. So number 2, alpha into 0 bar is equal to 0 bar. For example, if we take V is equal to R square, we have vector space with as usual operation, and if we take u-bar is equal to say 2 3 0 bar, as we know that 0 bar in u-bar is 0 bar is equal to what, 0 0, and take alpha is equal to what, 2. So what is alpha into 0 bar? So it is 2 into 0 0, which is equal to 2 into 0 2 into 0, and this is equal to what, 0 0, and which is nothing but the 0 bar. But we want to prove here, if we multiply if we multiply 0 bar by alpha, the output is what, again 0 bar. So here we can write this as, now consider alpha 0 bar. This is nothing but we can write 0 bar as 0 bar plus 0 bar. Here we consider this 0 bar as additive identity by using say a3, by using a3. Okay, now since again we know that alpha times u-bar plus v-bar is equal to alpha u-bar plus alpha v-bar. So we can write this as alpha 0 bar plus alpha 0 bar by using the property here, it is the property m1. Now if we add both side by now since this vector alpha 0 bar, since I am writing by using different color, say now since we can write in bracket alpha 0 bar lies in vector space V, and V is a vector space, implies there exist why this alpha 0 bar lie in V? By using say C2, by using C2 closureness property. So by using this property, from this we can write we can add the additive inverse of alpha 0 bar, which is what, minus alpha 0 bar, which is equal to alpha 0 bar plus alpha 0 bar plus minus alpha 0 bar. So by using again associative property, this is what on this side it is what 0 bar, since we add u bar plus minus u bar is what 0 bar, and this side we can write this as alpha 0 bar plus alpha 0 bar plus minus alpha into 0 bar. Here we use associative property, that is a2. Okay, and here we write at it as a4 additive inverse, we add additive inverse. But again, what is the value here? Alpha 0 bar is equal to this is what 0 bar, this is 0 bar, but 0 bar plus u bar is what, again u bar, so this is what alpha 0 bar, and hence we can write alpha 0 bar is equal to what, 0 bar. Next property, say third property. The third property is minus 1 into u bar. What is third property we want to prove here? The minus 1 into u bar is equal to minus u bar. Minus 1 into u bar minus 1 into u bar, minus 1 I am writing again here. So third property here, minus 1 into u bar is equal to minus u bar. For example, again if you consider an example, say v is equal to r square, and if we consider say u bar is equal to 2 3, as we know that what is the additive inverse of u bar? It is minus 2 minus 3, and you can get this as minus 1 into u bar, which is equal to minus 1 into 2 3, which is equal to what, since it is a one scalar and vector multiplication is what, minus 1 into 2 minus 1 into 3, which is equal to what, minus 2 minus 3, and which is what, additive inverse. This is nothing but the minus u bar. But we want to prove this. If we multiply any vector by minus 1, we get the additive inverse of minus u bar. You can check this also in above vector space. Which vector space? Here in R plus. If you want to determine what is the additive, what is the inverse of additive inverse of x bar, say x bar. So if in case of v equal to r plus, you can check here, say v equal to r plus, and we define operation x bar plus y bar is equal to xy, and alpha x bar is equal to x raised to alpha. Here we know that the here 0 bar is what, 1. 0 bar is 1. Now to find inverse, as we know that the u bar is equal to, say x bar is any vector, then say u bar x bar, then its inverse is what, x bar minus x bar is what, 1 by x, minus x bar is what, 1 by x, and you can get this as minus 1 into x bar is equal to x raised to minus 1, which is equal to what, 1 by x, and you can check here it is what, minus x bar. So minus 1 into x bar is same as minus x bar, but want to prove this. Now to prove this, again consider minus 1 into u bar plus u bar, and if this output is equal to 0 bar, then we can say that this is what then minus 1 u bar is same as minus u bar. Now we can write this as minus 1 into u bar plus 1 into u bar. So by using this is m4. What is m4 says? 1 into u bar is equal to u bar. So what is the value of u bar? We write u bar is equal to 1 into u bar. Now by using by using the property, I am writing by using different color, say alpha plus beta u bar is equal to alpha u bar plus beta u bar. So by using this is the property what, m2. So if you apply this m2 property here, then we get this is equal to minus 1 plus 1 into u bar. Now what is minus 1 plus, this is our regular real number, so we can, this is nothing but the 0 into u bar. But what is 0 into u bar? Just we have seen in here where 0 into u bar is what, a 0 bar. 0 into u bar is what, 0 bar. So this is nothing but the 0 bar. So we start from minus 1 into u bar, so minus 1 into u bar plus u bar is equal to 0 bar. So if u bar and say v bar is equal to 0 bar, then we can say that the what is, these are the v bar is what, minus u bar is equal to what, v bar. What is the inverse, additive inverse of u bar is what, v bar. So here, so from this we can write minus 1 into u bar is equal to minus u bar, or minus u bar is equal to what, minus 1 into u bar. And this is what we want to show here. Minus 1 into u bar is what, minus u bar. So now next last property, that is number 4. Last property number 4, why alpha into u bar equal to 0 bar, then either alpha equal to 0 or u bar equal to 0. Here you can say here why this minus, why I am not writing minus into minus 1 into u bar is u bar. I am writing, you can write this as u bar plus minus 1 u bar is equal to what, 0 bar, because it is a vector space. So this is nothing but so this is you can say here u bar plus v bar is 0 bar implies what is the minus v bar. Minus v bar is also u bar. What is, from this you can write minus u bar is v bar and minus v bar is what, u bar. They are the additive inverse of each other. Okay, for example 2 3 plus minus 2 minus 3. So what is the additive inverse of 2 3? It is minus 2 minus 3. And what is additive inverse of minus 2 minus 3? It is what, 2 3. So from this we can write what is minus u bar, it is equal to minus 1 into u bar. Now last, if alpha into u bar is equal to 0 bar, alpha into u bar equal to 0 bar, what we want to prove here, number 4, alpha into u bar is equal to 0 bar, then either alpha equal to 0 or u bar is equal to 0 bar. Now if alpha equal to 0, proof, if alpha equal to 0, then 0 into u bar is equal to 0 bar by using 1, since 0 into u bar is what, 0 bar, by using property 1. But if alpha is not equal to 0, we want to show that okay, u bar is equal to 0 bar, u bar is equal to what, 0 bar. Now consider alpha into, now consider since given alpha into u bar is equal to 0 bar, now multiply both side by 1 by alpha of alpha u bar is equal to 1 by alpha into 0 bar. But what is 1 by alpha into 0 bar? This side, this is what, by using second property, what is alpha into 0 bar is equal to 0 bar, by using this property it is what, 0 bar. And here on the right hand side is 0 bar, on the left hand side alpha beta u bar is equal to alpha times beta u bar. So by using this property we can write this as 1 upon alpha, okay, into alpha u bar is u bar, since alpha beta u bar is equal to alpha times beta u bar. But what is alpha into 1 upon alpha? It is 1 into u bar. This is what, 1 into u bar is equal to 0 bar. But 1 into u bar is equal to u bar, since by which property, say here by using m4. And therefore if alpha is not equal to 0, then u bar is equal to what, 0 bar. This is what we want to show here.